think that's recording properly. Okay, so we would like to predict stuff. This is chapter 15. Please start reading that. A bunch of fun things to talk about. And our goal is we want to make some educated guesses, some inferences about what we want, right? We want to predict the future. I have all of this stock price data. I want to know what's going to happen tomorrow. Like if the stock does this, should I buy? Should I sell? I'm YouTube and I want to recommend you a video that you're going to waste time on so that you'll watch ads or something. Like same with TikTok, right? TikTok knows all the videos that you've liked. Like we want to be able to predict the future. How does TikTok know which ones to recommend to you? Remember that we talked about that kind of at the start of the class this semester. How do you know, right? How do they know that we'll like it? Let me kind of remind you, or think about it in your mind for a second. Like, how in the world have you read about this? How does TikTok know that you're going to like this next thing that it's recommending to you? Well, kind of the idea is they're somehow mining that data, right? They know all the videos that you've liked, all the TikToks that you've liked, and they know other people that are similar to you at that point, right? They can find other people that have liked the same videos as you, and they've shown this new video to them already, and a lot of them like it. So that means they think you might like it. Something like that. That's kind of the process. So if you have enough data, you can do that for people. It's really cool. They're kind of putting you in a multi-dimensional space, and we'll talk about that. But like that's our goal. We want to be able to predict the future. Like given past knowledge, I want to like come up with some good, maybe not guaranteed facts, but some things that we think are probably going to be likely. Okay, so that's our goal. We want to make predictions, and we want to make predictions based on the stuff we've already collected. All right, so something that we're going to study in this chapter, at least get started with it in this chapter, is the idea of like, I've got all this data. It looks like this. You can kind of maybe draw a line through it. We'll notice that. Maybe draw a line through it, and the idea is if I see some new data, like I've got all this, I've saved all these facts, these X and Y points, and like I know that there's a really good line that kind of fits through that data. If I see another value, like right here, like if I see this X coordinate, the goal is to like, what in the world, what's the closest Y? What do we think would happen if we saw this X coordinate? Which one matches? Where would it fit on the graph? Where would be its Y? And so maybe right here, right? Maybe where this line meets. If we find a good line that fits, that's kind of the goal. We want to extrapolate, right? One way is to do that kind of thing. Another way is to, like I wrote here, one way is to like, all right, if this is my X, go and find the closest, I don't know, 4 or 5 points around that X. So like these guys. And then maybe like average them together. Like, okay, that's kind of around where the new point is supposed to be. So maybe I'll go in the middle of all that, and that ends up like right here-ish. Okay. So that's one way to do it. Another way is to actually calculate that line and kind of extrapolate, right? If that's possible, if they really do fall within a line. Like, okay, if I see a X value out here, like I've never seen it before, but I have all this previous data that shows a bit of a trend, so we can extrapolate, right? We think that point will probably lie maybe there. Does that kind of make sense? Any questions about that? Those are ways, they're hand-wavy ways, of course. I haven't shown you how to code it up, but like I hope you can imagine like that's useful, right? You see a new X coordinate, you want to predict the Y. Well, one way to do it is find things near, right? Find points with similar X coordinates and kind of average them together maybe, or maybe try to find a line that fits through them all perfectly and like the best possible one, and just put the thing on the line at that point. Okay, so those are ideas. And let's see. We've done this actually. We've actually already done this, right? From a previous chapter. Let's go and remember how to do that. This is, we want to make predictions, prediction based on values that are close by. So we did this before. I'm just going to remind you of it. We're going to do it all over again. And that was that like heights of children given their parents' heights. So that was table, read table. We've got data, it's family heights.csv, and I'll call that family heights. I forget which chapter we did this in, but we got all this data on these different families where we've got father's height in inches, mother's height in inches. We've got the heights of their children right here. And what mid-parent height means is like it's the average of the parents' heights. So mid-parent is just like the average of the father and the mother's heights together. These are all from the same family. That's why those are the same. Yeah, so yeah, you know that children don't have to all be the same. Like this was 4 separate children to the first family, but we can make some predictions based on this, and that's what we did before. So let me relabel some of these. Let's say that if I say relabeled and I give a couple things, mid-parent height, let's call that, and child height, let's call those instead mid-parent and child. Easier for me to type. And let's just get those. Like I've renamed them now, mid-parent and child. Let's just select out just those. So that's the mid-parent is the average of the father and the mother's heights. And then child. So let's get all those. And I'll call that heights. So okay, here's my heights table now. I've got the average height of the parents taken together and their child's height when they became full grown. And there is a decent trend. It's kind of hard to see, but it's still there. Let's do the scatter plot where mid-parent, the average parent height in inches is on the x-axis. You see that there's a bit of a line going through this, right? It's a little wonky, but you can see that for average parent heights that get larger, child height gets larger. You kind of see there's a bit of a line in that direction, but it's a little vague because different factors are involved here when people grow up. So what we could do is we've done this before. We've done this process of, all right, I have a new point, like a new child I've never seen before. How tall do we think they're going to be? Well, you give me their parents' average height. We can make that prediction based on stuff that we've seen. So go find similar parent heights within like an inch or so. And that's what we did before. So make a function called predict the height of a child, where you give me the height of their parents' average together. So mid-parent height is what they called it apparently. And let's just go and find all of the points that are near that. So go to the heights table where the parent average height values are between this new height. Like if we're asking for like 60 inches or something, maybe we can find like the average parent height was 60 inches. Let's go find all the points that are between like 59.5 and 60.5 inches. So just like an inch around that are between mid-parent height minus half an inch and mid-parent height plus half an inch. This is what we did last time when we considered all this. And those are like all the close points, right? Taken together. Those are all the points near that height that we're trying to predict for a child we don't know how tall they're going to be yet. Like the child's still young. And if we go there and we just maybe take the average around all that, that would be a good prediction, right? That's what we've done. So those points go to the child column. So these are all the child heights for the parents that are similar to this new parent's height, average parent height, within an inch. We know all the heights of their children. That's in close points. Go and get the heights of their children and take the average. Like that is a good approximation of what we think that the child's height may become. So like if we got 71 inches, let's say, so that's like around here, 71's in the middle. So like let's say we've got a new child with that height, or a new child that we don't know how tall they're going to be because they're still young, and we know that their parents' average height is 71 inches. So what we're going to do is we're going to go and find all these points. Take all of these guys between like 70.5 inches and 71.5 inches, like here to here, all those points along this line, and take the average of their child's heights. So all the y values. Average together all these y values, and that's a good approximation of what we think the child's height might be. And that's about in the middle here, so 67.7-ish inches will be our prediction. So that kind of makes sense. That's what we did before. It's kind of like find all the ones similar within a range, average them together. And like that's a prediction. So yeah, let's attach our predictions to the table. That's what we did. Sorry, it's heights, plural. And so let's add a column that is the prediction for each of the things and see how close we were. So take heights, add a new column, prediction, because we have a function now that could take a mid-parent's height. So if I apply this predict child function or predict height function to the mid-parent column. Oop. I can make, I guess that's going to take a second. I can make this table, I'll call it heights predictions. And so it's not perfect, but it is like the average of things. And so for an average family height of this, we're predicting that the child's going to be not as tall. And yeah, it's kind of average together all of their children's heights in a sense. Same with these guys, right? We're going to predict that this child height is going to be that, but it's a little bit off sometimes. All right, it's never perfect because it's an average of a bunch of children, but it's kind of the best one for some definition of best. All right, and so we can make a scatter plot to kind of show what we've just done. Heights with predictions, scatter along where mid-parent is on the x. And so what we've just done is for like, here's all the child heights, and then we've got the predicted height of each of those child heights. And it's kind of like a line. It's kind of like the best line that goes between them, if that makes any sense. Okay, so that's what we've done before. It's just like, you give me a child we've never seen, I'm just going to find similar parents and use their children's heights to predict this height of this child. We have no clue how tall they're going to be yet. And like just average together the heights of all the children of parents with similar heights. That's what we did. Okay, and so we get some decent predictions, and that is one way to predict the future based on things that you've already seen. That's kind of the point. You're learning from your data. It's machine learning, right? You're learning from data that you've already got. Any questions about that process? This is something that we've seen in the previous chapter, a long time ago. Because now I want to kind of talk about this idea, this other option of like, all right, let's kind of find a line that goes through this data and use that as a prediction. Because you can kind of see that there is a line apparent here. It's we're not getting an exact line right now, given the way that we've calculated these predictions, but there is maybe a good line that predicts these heights. And so, yeah, let's talk about the process of just prediction in general. The process is called regression. If you've taken a statistics class, you've heard this word for sure. But the idea of the word regression is just, it's the process of using one value to predict another. Like you give me an X value, I want to predict the Y value based on data that I've already seen. And the etymology of this word is kind of interesting because, you know, like the word to regress means like to like go back, right? To like not be as powerful, to not be as good, kind of. But it comes from a fact of biology, and we kind of noticed that in real life. You had some very tall parents here. Look at this average height. Very tall parents. None of the children were ever that tall, which is interesting. None of the children ended up being as tall as the parents were. So that's an interesting fact of biology. The heights of descendants of tall ancestors tend to regress downwards towards the average height. That's apparently a fact of biology. So I guess if you have tall parents, it's not necessarily the case that you're also going to be tall, interestingly enough. But you'll be taller maybe. But yeah, now we just use that word to mean predicting. It's not like you're going back to some previous state or something. It's just like we use the word now to mean prediction, but it came from that thought. And yeah, the kind of regression that we just did, because we did a prediction, right? We're predicting child heights given the heights of their parents, the average height of their parents. That was a regression process. And we found, the way that we made our predictions, we found similar parents to the one we want to predict the height of their child. And that's called nearest neighbor regression. All right, so that's the kind of that we just reviewed. And it's called nearest neighbor because it's like here's your house, like we want to predict 71. Go and find all the neighbors to 70, like within an inch. Like here they all are, and average together all the different Y values because that can be our prediction. All right, so you kind of group together the X values you're trying to predict, right? go find close enough x values within some range and average together the y values, and that's your prediction. Okay, so that's what we did. That was regression. Okay, that was regression. The other option is go and find the line. If there is a line that kind of goes through this, that's another standard way of doing that. All right, we ready for that option? That's the new thing. This was called nearest neighbor regression, this process. So yeah, if we're good, let's talk about the next option. So a lot of the time, maybe not so much this example, but you can kind of see that there is a line here secretly. It's just not very apparent. A lot of the time, though, data, when taken together and you graph it out, you'd make a scatter plot, it looks like a straight line. Like sometimes your data legitimately looks like this, which is nice. Or it could even be like this, right? You can see that there's a trend going on, upwards or downwards, that's fine. But there's a way to come up with a number to express how closely our data resembles a line. And that's a useful number to us. All right, it's called the correlation coefficient. For some reason, they're using the letter R in statistics to represent that, but it's called the correlation coefficient. It's just a number that measures how tightly your data is on a line. All right, measures linear association. So some data does not look like a straight line. I'm sure you can imagine there's some kinds of data that look like this. Like you got your, I don't know, boop, boop, boop. Whee. Like this is what your data looks like, and like the best thing that goes between this is kind of like a quadratic curve, something like that, or like the graph of a logarithm. Some patterns aren't straight lines, but some are, a lot are. So this process works for patterns that have straight lines in them, and this is a number that you get back if you run your data through this process that calculates the correlation coefficient. You're going to get back a number. It's based on the standard unit, so using converting everything into like distance away in terms of chunks of a standard deviation away from the mean. And the value that you get back when you calculate this R value, this correlation coefficient value, is between -1 and +1. So if you get a value that's exactly 1, that means all of your data is perfectly on a straight line. -1, perfectly increasing straight line. If you have a -1 R value, that means your data is along a perfect decreasing straight line. And if your R value is 0, that means your data does not look at all like a line. It's just, there's no upwards or downwards trend. And so here are some examples of different R values, different correlation coefficient values. If you had a data set, you could run it through this calculation, and you could get these values, and you can see what it means for the data. So if your correlation coefficient was exactly 0, there's no line, right? There's no trend in any direction. They're like, it's just like perfectly symmetric, right? It's like it's on a circle almost. This is R equals 0.2, so it's a bit of a positive linear association, but it's not very strong. That's what that is, right? Here's 0.5, R equals 0.5. That's starting to look a lot like this, right? You see that there's a positive linear association, but again, it's kind of ups and downs. It's not perfectly along a straight line. But as R gets larger, this is just a number that you can calculate based on your data set to even before you look at it. You can see that R equals 0.8. That's getting closer and tightly packed together, right? So that number tells you a whole lot about whether or not your data is linearly associated, which is nice. Here's R equals 0.99. It's like almost perfectly along a straight line. R equals 1, they'd all be on the same line, which is cool. And so that's those are positive values. For negative values, it's the same idea. Like -1 means it's a perfect decreasing straight line. So this is R equals -0.5. You see that it's along, you see that there's a trend, but the trend is decreasing. It's a linear trend, but it's decreasing. It's kind of the opposite of this one. Okay, so yeah, that's what the correlation coefficient can tell you. It's just a number that measures how close the stuff is along a straight line. Okay, any questions about this idea before I show you how to calculate it? So it's a nice number, right? It would be nice to have this, this as an option. Well, let's talk about it. Correlation. I've got a fun little function that just kind of makes up graphs of things. So let me show it to you. You don't have to study this code. I've got a little function from the textbook that makes a little scatter plot. It kind of makes a, where do I want to be? I want to be here, does not copy automatically. It automatically makes a scatter plot. It makes up a data set with a certain R value, which is kind of cool. It's called R scatter. You don't have to understand how it's made, but if I give a R value of 1, this is what it looks like to have a data set with an R value of 1. Everything is perfectly along a straight line, okay? Whereas anything smaller than that, R scatter, like 0.8, is not as strong, but it's still decently linear. Right? That's an R value of 0.8. This function made up a data set that has that exact R value, which is kind of cool. So that's what a positive linear association looks like. Like if you had a data set, this is an example of a data set that has a negative R value, negative 0.7. So it's still a strong linear association, but it's in the downward direction. As the X gets bigger, the Y gets smaller now. Okay, so that's what that means. So no linear association is an R value of 0. It's like everything, there's no line between any of this. There's no prediction that you can make here. They're all just kind of like spread out in a circle. Okay, so yeah, let me, do we want to calculate it yet? Not quite. So I just want you to try to look for linear association because that's something maybe you haven't looked at before. You haven't thought of it before. So let's read in a table and have you try this. So I've got a table on in our data folder. Please go and get it. It's called hybrid.csv. It's a data set on hybrid cars. Here's the data set, and if I just take a little sample to show all the different options, this is a bunch of different cars. I think some of them are hybrids, maybe some of them aren't. But you've got all this data on them. You've got what they are, what year they were made, how much they cost. You got some data about like how fast they accelerate, like 0 to 60 in how many seconds probably, what their miles per gallon is, and then what kind of car are they? Are they an SUV? Are they a compact car? I don't really know what these differences are, but they mean something, I'm sure. So go get this table, include it, and I'd like you to try to make some scatter plots. Here's my question for you. Try to, I'll give you a few minutes to play around. Go and look for some linear associations between data. So like go looking for go scatter all the different numerical quantities together, X values and Y values, and try to find some linear associations of all the rows in this table. So make some scatter plots. Also remember how to make scatter plots. And see if two variables correlate with each other. So give that a try. So read in that table, and you've got a bunch of different numerical values, right? You can only do scatter plots with numbers. You can use the year, MSRP, acceleration, and MPG. Try every possibility, and go see if there's any correlation. That's in the word, right? If any of those variables are correlated with one another. Try to put the year on the X, the MSRP on the Y, every other possibility, and see if you can find any linearly associated values. Maybe as the year goes up, everything gets more expensive. That would be a positive linear association, right? But also you might find that some things are not in a straight line. Some things are, you see that there's a pattern maybe. Some things may not have a pattern, but some things may have a pattern, but that pattern might not be linear still. Isn't that interesting? So yeah, I'll give you a head start on this. Give this a try. And then we'll learn how to calculate the actual R values. And remember that R just means correlation coefficient. I don't know why they called it R. But it's a measure of how linearly associated the data is, either positively or negatively. And I guess you don't have to do every single possibility, because like if you did year on the X and MSRP on the Y, it's just the inverse. It's the mirrored graph of MSRP on the X and year on the Y. So you only have to do half as many as you think you need right now. Did I do that right? Yeah, let's see. Does anybody find any good ones? Some good linearly associated variables. Oh, nice. Yeah, let's do that one. Acceleration and MSRP. And it didn't have to be this one on the X, this one on the Y. It would be a very similar graph if I swapped these two. I think you can imagine. Yeah, I totally see a positive trend there. Does everybody see it? Everybody agree? Nice. So it looks like if you want a... this is actually interesting to me. A car that's more expensive, because I assume acceleration means it's like it takes longer to accelerate, or maybe it's like, I don't know what that means anymore. I don't know what the acceleration value means, but maybe like the car is heavier when it's more expensive, something like that. It is harder to accelerate, but that's okay. But that's an interesting thing that we've seen. So it looks like if there's more acceleration, then the car is more expensive. Maybe it's a measure of like how fast the car can accelerate in a positive way. I don't know. Any others? Do we notice any other trends? We can try some as like year in MSRP maybe probably is useless. But you never know. Looks like, yeah, you don't see a super good trend. It's a little bit increasing. It's like as the years go by, inflation, maybe. But there's others, right? You've got definitely miles per gallon and cost are probably somewhat related, right? That makes this is again interesting. It looks like the more expensive the car, the worse it gets on miles per gallon.
Maybe it's SUVs.
Oh yeah, we'll have to look into that. Yeah, SUVs. SUVs make it worse. Yeah, but also maybe like if you're rich and you're gonna buy an expensive car and it goes fast, you don't really care about miles per gallon at that point. Yeah. So again, this is another trend, right? This was a positive trend. Yeah. This is the opposite, right? This is a negative trend. And honestly, this graph doesn't really even look linear. Like I see, you can maybe draw a line, but like if I drew a line between these points that kind of made sense, I'd like go into this gap here. I think it's more of a like that, like a 1 over x kind of graph, you know? And so there's a trend going on, but it's not necessarily linear. When you have a trend that isn't linear, you can still try to calculate this R value. It's just trying to tell you like, oh, this is how closely your data is all along a straight line. But if you have a pattern that's not a straight line, your R value might mislead you. It really is looking for a perfectly straight line. So you'd still get like a decently negative number here if we were to calculate an R value, and we will eventually. But you're going to have to look at the graph again and be like, oh, actually, this isn't linearly correlated. It's a different kind, okay? So, yeah. Let's see. Another fun thing, if we consider just a certain kind of car, like SUVs, that's something that your book did, let's talk about them. Some of these trends look a little bit different, or they're cleaner at least. Because some cars, like, I'm sure there's sports cars in this data set that are kind of throwing off the numbers. So if we just consider a certain kind of car, where the class was SUV, and then if we do like a scatter plot again, if we did miles per gallon and MSRP, then we do see more of a linear trend. So some of the other kinds of cars were kind of ruining this deal for us, but SUVs in general, it's like, all right, the less expensive the SUV, the better it gets in mileage because it's probably a lighter thing. Probably doesn't have as much material in it, which is interesting in itself. So there's that. What else did we do? We did acceleration, MSRP. We'll probably see that same trend. Yeah, we saw a weird trend. We saw we saw an increasing trend. Acceleration, MSRP. I'm assuming maybe acceleration doesn't have to do with 0 to 60 anymore. It's probably just a number that means like a bigger number means it can accelerate faster or something, probably. And so for SUVs, at least, you see that, all right, as they get more expensive, their acceleration increases. Maybe that's what that means. Something like that. But we still see the patterns, and sometimes they get more linear if you just consider certain kinds. Like there are other kinds of cars that were making this non-linear, but the trend, at least for SUVs, seems to be linear for miles per gallon and MSRP. Same for acceleration and MSRP. So interesting, cool. Let's see, what do I want to do? I want to teach you how to calculate this R value. Like, that's the first thing. What do I want to do next? I guess I want to show you the way that we calculate the R value is going to be based on standard units. So remember what that is? That's from the last chapter. That means that's a number that describes your data in terms of how far away was it from the average, from the mean value of the data set, in terms of standard deviations. How many standard deviations was your data point away from the mean? And that's what standard units means. So let me show you that if you turn your data set into standard units, it doesn't change these graphs that we're looking at. Because that's the first thing we need to notice. Like, all right, if this R value calculation is based on standard units, I don't want that to ruin anything for me. So let me show you that it doesn't ruin anything, and we'll go from there. Okay? Let me, I guess I can steal from last time. We made a function, right, that turns something into standard units. Standard units. Come on. Yeah, here was our function that did that from last time. There's a function that you give me some numbers. I'll turn all of those numbers, that array of numbers, into another array that's in terms of standard units this time. So take all the numbers, subtract the mean from them. So how far away are they from the mean? What is their deviation from the mean? And how many standard deviations away from the mean are they? So you divide by the standard deviation of those things. So let's look at that in terms of my SUV table. So I've got a few different columns. Let's do the miles per gallon column. So here's the normal miles per gallon in terms of all these for all these cars, but we can turn that into standard units. Take all those numbers, turn them into standard units, and so like 31.99 was really, from the mean of all these values, 1.32-ish standard deviations above the mean. So that was a good one. That was pretty cool. And so these are all like one or -1 standard deviations away from the mean, which is nice. And let me turn these values into standard units. Okay, let's take, gosh, how do I want to do this? Yeah, let's turn these values into standard units. I'll say SUV, give me, let's select out miles per gallon and MSRP and acceleration. So these are just the values that we were graphing for all these different cars, for all these different SUVs. And let's convert all of these columns to standard units instead of whatever their normal values were. So let's do with columns. Let's do MPG in standard units. Honestly, I want all of these in standard units, so let me copy and paste. That MSRP we're going to put in standard units. So I just need column names, and I'm going to copy and paste to make it easier on myself. Boop. And then how do I get MPG in standard units? I get that column out of the SUV original table, and then I call standard units on it to convert everything. So I did that one, and the rest of these are similar. This one is MSRP. This one is acceleration. From the original table, convert it into standard units, please. And I'll call this, I don't know, SUV2. So I've just taken the original table and I've turned this column into this one. this column into this one, this column into this one. And you see, first of all, that this puts all the values on an equal playing field, which is really nice. Like MSRP was in the tens of thousands, right? But now it's like, how many standard deviations were these prices away from the mean? Like, all right, this one was negative 0.26. This one was like negative 1. This one was a little bit more expensive than average. All these values now are like between, for all of these different columns, are now between like negative 2 and positive 2. Because we learned that that's what happens when you calculate standard units of any data set. That's what it gets turned into. And so all these data are now kind of, they have the same unit now, and all those values are similar to one another. It's not like this one is like between like 20 and 50. This one's not between like 20,000 and 50,000. They're all between like negative 2 and 2. So like that's useful already. And let me show you that if we did these same graphs, like our original one was, let me prove that to us. Let's see them all together. I'll put them on a slide for us. We originally did MSRP and MPG of the original, where was it, SUV table. So like we had this, I guess I can probably copy this, right? Copy output. Is that gonna work? Yeah, cool. That was that one. Then we did acceleration. Yeah. So these were the originals with their weird units. But let me show you that converting them into standard units didn't change anything. So let's do, again, an SUV2 table. Let's do a scatter plot of, what was it? MSRP versus MPG. So MPG on the x-axis, which is, we want to do MPG in the standard units column. So I don't want to type that out. So 0, 1, 2, column 3, and then MSRP, which is column 4. Look at that. That's a similar graph, and for some reason your book changes the way that this gets plotted. Let's put them all on an equal playing field. So like negative 3 to positive 3, we know is what the x values are going to range between. 99.97% of them, right? If this is a linearly, or if this is a normal distributed thing. So like here, there's the graph. There's the same graph, but it's in terms of standard units. And look how it really is. It's this one versus this one. These are the same graph, but this one was in original units. This one is in standard units. You see that nothing changed except things kind of got squished around a little bit. Nothing at all changes, so the trends don't change. The trends don't change. We'll do the same for acceleration MSRP. Let's make this one again. Where did I want to be? That was acceleration is column 0, 1, 2, 3, 4, 5. And I still want MSRP on the Y, so 4. So there's this one in terms of standard units again. So do you see how this graph, where I've turned all the data into standard units instead of their original units, I still have the same picture. Like this picture is still here, right? Maybe things are a little bit squished or spread out. That's okay. But you see that there's still a trend going on. There's still this trend. There's still this trend. Maybe it's a bit sharper because the things got squished or spread out than their original units, but it didn't get taken away. Okay, it didn't get taken away. And so that means it's okay. If we want to calculate this R value, it's not going to matter that we're turning things into standard units to make things easier on ourselves. Okay? And that's what we're about to do. So, are we ready to learn how to calculate this number based on our data set? Like how to calculate the R value, the correlation coefficient. Any questions before we get there? Because that's the last little step here. Let's do it. The way it works, here is how you calculate R. You first convert everybody to standard units, and then you multiply your two variables together. So you had a bunch of x values and y values for your data set that you're graphing, that you noticed there was maybe a trend. You want to know the R value. You're going to multiply the x and the y values together, add them up, and take the average. Only when you've converted to standard units, though, does this do something. And so that's how you calculate the R value. First, convert everything to standard units, then take the average of the products of the variables that you're trying to figure out their correlation coefficient. And so do remember that it's only going to try to measure linear association. It is going to, your R value is going to try to calculate how closely your data fits on a line. So when you have truly linear data, the R value is going to be decent. It's going to look like this, right? It's going to try to predict that line. It's going to be like, yeah, like 0.8 or something. When you have nonlinear data and you try to do this calculation, it's still going to try to find a good line that fits through it. And sometimes you might get a good value. Like this one, like what's a line that fits through this? There's still a decent line that fits through this, right? But also notice this was not supposed to be a line. So you're going to have to graph it eventually as well. But the R value is a good first step. So if you, this will still give you like R equals 0.7 or something probably. But you need to notice that R probably wasn't the answer here. You don't want to do, it's not a linearly correlated thing. And then if you have a data set that looks like this, like it's very clearly correlated, right? You still see a trend. There's like this kind of trend. But the R value is kind of trying to measure linear association. It's going to try to find the best line that fits through this. And it's like, it'll find this line, right? And there'll be no association. That's what it's going to find. But really, there is an association. It's just not linear. All right, so the R value can't solve all your problems, but it's a good first step. It's a good first step. So let's learn how to calculate R. Let me show you what I mean by all this. And we'll get some numbers for all these things that we've been doing. So calculating R. Calculating R. Boop. So let me make up some X values. Let's get the values from 1 to 6. And let's say the Y values are these. Just a made-up table. I made up a thing that I want to graph. So let's make a table with the X and Y columns. So I've just made up some data so that we can do the process on this sample data. So take the X values, take the Y values, put them in a table, and I'll call this table T for short. So I've just made this table. I've got X values and Y values, like this X value and Y value go together, same on down the line. If I do a scatter plot of these, where X is of course on the X, and Y is of course on the Y, let's make some big red dots for fun. Here is my graph. All right, here's my data set that I just made up. You see that there is a decent linear trend, right? What's the line that goes through this? It's like that, in the middle or something. So there's a decent linear trend. If we were to calculate the R value, you'd probably get that, all right? Something that's decent, but not perfectly 1.0, okay? So the way that we calculate the R value of this data is we turn everything into standard units. It's kind of like, again, just like we were doing for standard deviations, you kind of read this definition backwards. Get everything into standard units, multiply the X's and Y's together, and then take the average of those multiplied values. So add them all up, divide by how many. And so let's do that just manually, and we'll go from there. All right, so let's turn all these columns, this T table, let's get X into standard units and Y into standard units, because that's the very first step. Right, we've got a function that does that. So let's take T, let's add those columns to it. Let's turn X into standard units. And that's, I'll just call my standard units function on the X array, which is nice. We could do that. And I'll do the same for Y. The same for Y. Standard units of Y. Oops. And I'll call this my table T data in standard units, SU for standard units. Cool. And so here's the X values in standard units and the Y values in standard units. The second you've done that, you can now get the products of these, right? So we want the average of the products of the two variables when they're in standard units. So my next step, if I want to calculate R manually, I'm going to show you, there's a function for this, it's very quick, but we're going to do it manually once. I just multiply these together, right? Multiply those together, these, multiply those all together, and I'll take the average of those products. Those are products of your standard unit values. So let's take this table, dot column number, this is 0, 1, 2, take column 2, multiply all these values by column 3, right? The Y in standard units. That's the first step. These are a bunch of products of standard units, okay? Let's add that in. It's product of standard units. Take all those bad boys and let's tack them onto our existing table. I guess I'll call this something, T product. Boop, all those guys. And so that's almost it, right? I've got these products of these values, right? Product of these. Now I just take the average. Then that's my R value. That's all you do. That's how you calculate it. So the R value is, finally, you go to that product column, T product, column number, I don't want to type it out, 0, 1, 2, 3, 4, and I'm going to take the average of all those values. So it's np.mean or np.average of all that. And so finally, my R value for this data set is about 0.6. And that's how you calculate it. That's how you calculate the number. You can imagine if they're all in a straight line, they'll multiply together and they'll all kind of be the same numbers together, like the positives with the positives, the negatives with the negatives. If it's in the opposite direction, one's positive, one's negative, that's why it becomes -1, right? One goes up, the other goes down. Hope you can kind of see why this definition makes a little bit of sense. It is a little beyond the scope of the class to explain it, but that's how you calculate it. And so if you want to calculate a correlation coefficient, you just do this. You do this process, and we can turn that process into a function. All right, let's make a function called correlation. I want the correlation of the x and y columns of a certain table called T. So you give me the table, you give me the names of the x columns and the y columns you want to find the correlation of. Then what I'll do is, well, I'll do this process, right? Let's make a function that does this for us. Let's turn these things into standard units. So go to T, get the column that was called x. Go to T, get the column that was called y. Turn them into standard units. I've got a function for that, right? Turn them into standard units. So now I've got them both in standard units. And then I multiply them together, right? And take the average. Multiply them together, take the average. It's a long process, but you can spell it out in a function, give that back. So that's now once and for all how we can find the correlation coefficient. What's the R value for a certain, my table was actually called T, right? And the x column was called just x, the y column was called just y, and there I am calculating it all in one fell swoop. So does this function make sense given the definition of how to calculate it? You see how it's doing exactly this? Average of the products of the two variables when they're measured in standard units. Just that gives us our correlation coefficient. That's pretty neat. And so now we can finally calculate correlation coefficient values for like these tables. We noticed that there was a linear trend for the SUVs at least, for the miles per gallon versus and the MSRP, and then the acceleration in the MSRP. One was negative, the other was positive. Let's see how strongly correlated they are. What's the R value? What's the correlation coefficient for those guys? So I can give my function, I can give it the SUV table, and we did MPG and MSRP. I can just give the original units because it's going to calculate standard units out of them. Just that's how the function worked. So this one was negative 67, or negative 0.67. And so that's negative, right? You see how that's like kind of close to -1, but not super close. And so it's decently correlated in the downward direction. When one goes up, the other goes down. So that's what that means. MPG, MSRP is correlated like almost 0.7, negative 0.7. That's a negative correlation. All right, so there's that one. And then we could do acceleration and MSRP. That one was not as correlated. You see that there's some, like these dots out here are kind of ruining the line, but it's still, for either one, right? It's still positively correlated. So it's a positive value that we get back, but it's almost about 0.5. And so it's decently correlated, but not perfectly correlated. So it looks like there's a stronger trend for MSRP and MPG than there is for MSRP and acceleration. But we can get a number. That's the whole point. Isn't that fun? Are there any questions about that? You want to see what that's doing? So it's a nice number that kind of tells you how strongly this data is packed together on a line, which is very useful. Very, very useful. Notice, given the definition, that it didn't matter the order. If I did correlation of MSRP and acceleration, I'm going to get the same value back, right? Because when you multiply, it didn't matter the order that you gave things in. So I get the exact same thing. Even though the graph's going to look mirrored, it doesn't matter. It doesn't matter, you get the same value back, all right? So correlation is nice, but remember that it only works for data, where was I? It only works for data that is like linearly associated. It's giving you back a value, a number that represents how linearly associated the stuff is, all right? And so if you give it data that is not linearly associated, you might get a weird value back. It might say that, oh, we're not correlated at all, but it's just a different kind of correlation, all right? So let me show that to you. Let's make up a data set that's not linearly correlated and see what this, like, what do we get back as R? I'll show that to you. Let's do this. Let's make a non-linearly correlated data set. Let's say, let's do the graph of x squared. I think that would be a perfect one. It's like it's a little parabola, right? Let me show that to you. So let's make some x values between like -4 and +4 going up by 0.5s. And here's my nonlinear table that represents this graph. Let's do x values are these new x's between those things, and then the y values can be those squared because I want to make the y equal to x squared graph. All right, that's my nonlinear values. So for every x, this is the y, you square it, and let's scatter plot that. So x is on the x, y is on the y, and let's make some big red dots again. So here's my new table. It's called nonlinear. So it's a nonlinear data set, right? The x's and the y's, they're correlated, but not linearly correlated, all right? So if we want to calculate the linear correlation coefficient, we're going to get a weird number back. So correlation on this nonlinear table, where x is the name of the x column and y is the name of the y column, I want the correlation between the x's and the y's. I'm going to get the number 0.0 back. So that our correlation coefficient, it's thinking that there is no correlation between the x's and the y values for this data set. You see that? And that might lead you astray if you didn't do a scatter plot. Because what it's trying to do is like, what is the best line I could draw between these? I don't know. It can't go up, can't go down. It kind of draws a straight line. And the correlation coefficient is, in essence, a slope. If you think about it, it's really just a slope. And it's like, what's the slope of the best line through this? 0. And so it's trying to tell you that there is no correlation, but it's just the values are associated together, just not linearly associated together. Does that make sense? Any questions about that? So that's kind of how that works. And so you do want to make the graph, in addition to doing this correlation coefficient value, make sure it was a linearly, like, make sure there was actually a linear trend going on. Otherwise, this function will give you back something weird. Like 0, even though this is perfectly correlated to x squared, right? Y equals x squared. We just didn't know that, all right? So, yeah, depending on what your data set looks like, you can kind of see this one was like -0.6. This one was +0.5. And the reason it was +0.5 is because there were like some dots not pretty far away. Like this one, they were pretty tightly packed, but like this dot was kind of ruining things, right? This dot and this dot, they weren't really close to the rest. And so these two dots were kind of bringing down the correlation coefficient. And so depending on the size of your data set, the bigger the better. This helps it out. But if you had a weird table with some, like an outlier, that might change what your correlation coefficient becomes, because it gets harder to draw a good line through all of your data. So you got to watch out for that, and maybe clean up your table. If you see like a clear outline, you might want to get rid of that before you calculate your R value. So let's make some new x values and y values. 1, 2, 3, 4, 5 x values, and then the y values that are associated with those can be 1, 2, 3, 4, and 0, let's say. And then let's do a scatter plot of that in the same kind of way. So here's a new table called outlier. It's here's some data, 4 data points that are perfectly along the line, right? If I just considered those, R value is 1.0, right? Perfectly along a straight line. But then here's another outlier. Here's a little dot bringing everybody down. right? Way out of the line that is on the rest of the data. Okay, so a bigger data set would solve this a little bit, but I just want to show you the problem here. Correlation. So here's my table. It's called outlier, and the x column is called x. The y value is called y. What's the correlation between the x and the y values? 0. This was a carefully crafted data set, of course, but you can imagine the same kind of problem is going to happen to you maybe one day. So like you had a perfect 1.0, R was 1.0 trend here, but an outlier ruined the day. See that? So you might want to clean up your data set, all right? You might want to clean up your data set before you do this correlation calculation, because then it might make things better for you. You might see the true trend, right? Because you know this would have been 1.0 if you excluded that one. So I do like outlier where the x values are below 5. Then there's a perfect 1.0 correlation between all that data. This was a tiny data set. You can imagine that was on purpose. That ruined things especially badly. But outliers in general, right? That's what kind of brought this from a higher number down to like positive 0.5. And that's what kept this one at like negative 0.6, right? So this one, like that was an outlier. That brought down the correlation coefficient. So if you see an obvious issue, you might want to get rid of it. Okay? So I think that's what I wanted to say about all that. So this is the correlation coefficient. It's called R for short, and it just gives you, it's just a number that we know how to calculate now that measures how tightly packed your data is along a line. And that's useful sometimes, like what is the trend? Is there a correlation between these two variables? A linear correlation. That's what it measures, all right? And so we know how to calculate it now, and that's pretty nice, all right? So do keep in mind, again, correlation is not causation. That's the motto of this entire semester, right? So here's another fun graph that kind of makes that clear. So here is if you just don't even think about what's on the x and y right now, here's a data set that is pretty positively linearly correlated, right? These values are pretty clearly along the line. Maybe Germany's an outlier, I don't know. But like you see a straight line, yeah? Maybe Sweden's another outlier. Here is what it's predicting, or what it's trying to say is, on the x-axis for each country, there's the chocolate consumption, like on average for people. And then on the y-axis is how many people won a Nobel Prize after you like account for the population differences. And so it looks like the more chocolate that you eat, that the country on average eats, the more Nobel Prizes the scientists in that country get. So I guess does that mean that we should all be eating chocolate? Because then we'd be smarter and we'd have more Nobel Prizes given out to the United States? Probably not, right? There is totally correlation going on here. It says, here's the R value. You know what that means now. The R value is like 0.8 almost. It's a very strongly positively correlated thing along the line, but there's probably something else to it, right? It just happened that the Swiss love chocolate and also they love science. It doesn't mean that one caused the other, right? But maybe it does. Who knows? Maybe that means we should all eat more chocolate. So yeah, just keep that in mind when you're dealing with all this stuff. You still have to do a randomized controlled experiment, make sure there's actually causation going on. It's not enough to just be correlation. Okay. So any questions about any of that? Does it make enough sense so far? We've got a new number that can tell us some cool things. So if we're all right, let me give you all the code that I've written so far, because I want you to like use these functions. Use the correlation function that I made here. It's like go and get it, copy and paste it if you need to. So if you refresh the code from class, you should have the chapter 15 file now. And I have a question for you to try. Here's my question for you. Please try to, let's see. Go through the Sun's Heights dataset, so the sunsheights.csv file, import that, read it into a table, and try all the different variables to see how they correlate, right? Because maybe like, all right, tall people, tall mothers have tall children, tall fathers have tall children, or tall mothers and fathers, they correlate well together. Tall people have kids with other tall people. So try to do calculate the correlation coefficients, because we have that function now, for all those different pairs of data in the sunsheights.csv file. So if I go back to that, that was up here somewhere. Or this was family heights. I want you to do sun's heights only this time. So it's almost the same. So let me read in the data set, and then we can look at the column names real quick. So let's do that. And it's sun's heights. .csv, sun's heights, instead of family heights. It's a different one. So we've got father height, mother height, and son height. Try every pair, right, of these three variables and see how they correlate. Father, mother, father, son, mother, son, right? You don't have to do them in the other direction, because that would just be the same value, right? Because we know it's a product of things. Product doesn't matter. If you do A times B is the same as B times A. It doesn't matter which order. Which then you say is the x-axis, which then you say is the y-axis. It matters in the final graph, but not in the correlation code. Try to find the, not the actual question back up, but try to find the correlation between all those different columns, and maybe try to calculate correlation the hard way just once to remember how to do it. Try to find the most strong. I think we already did, by looking at the graph, we could tell what the strongest correlated things were in this data set. We did that once, but now we can have a number to go along with it, which is kind of nice. I'll give you a couple minute head start on that. You see which one has the strongest correlation. All right, that's my timer. So let me do it too. So I've got this table, and let's do the correlation. of all these guys. Correlation between father and mother. Again, you don't have to do correlation mother-father separately. It would give you the same value, right? So, oops, I need the table itself. I need to give it son's heights and then the names of the columns. It looks like there is not very strong of a trend. It looks like sometimes the taller the father, the taller the mother, but not necessarily the case that tall people get together with tall people. So that's interesting in itself. So very, very weak correlation, probably not really meaningful if you do the actual graph. But that's cool in itself to notice. Father and mother not very correlated. Then you got like mother and son. The mother's height, how does that affect the son's height? How correlated are they? Not super correlated. You see that there's a positive trend, like 0.31. When the mother's height gets bigger, so does the son's height. But it's not a very strong trend. All right. Then the other option is father-son. And that was the strongest one. So it looks like the father's height is the best predictor of the son's height. That's how you can interpret this. Does that make sense to us? You would still, of course, have to do the graphs and make sure, like, is there a line going on here? Was something else weird looking? But we see a strong correlation value, so maybe we should graph it. Let's do father and son. Father on the x, son on the y. Yeah, that seems like it's a linearly correlated thing. It's got a 0.5-ish R value, which makes sense. I see a positive, like as father's height goes up, so does the son's height usually. And it's not perfectly along a straight line, so it's not a 1.0 correlation, but it is a decent one. All right, so there's that one. And if we wanted to calculate this manually again, remember what we do to calculate the R value. Get everybody in standard units, multiply together the values of the variables, and then take their average after like adding them up, divide by how many, okay? So let's get the father heights as standard units. So that's son's heights table, get the column called father, so we're just doing it manually for once. So that's the father heights. If we want that in terms of standard units, we could say standard units on father heights. We have a function for that. Or we could even do that one manually. So like, how do I convert this father heights column, right? It looks like this. Father heights. Here are all the father heights. How do I convert those to standard units manually? It's you take them all, you subtract from the mean, right? So subtract the mean from that. And mean father heights. So this is all their deviations from the mean, but we want them in terms of chunks of standard deviations, right? How many standard deviations away from the means are all of these? So divide by MP dot standard deviation on father heights. So these are the standard deviation values. It looks like we have a very, very tall dad in the very first one. That's interesting in itself. So these are the father heights and standard units now. Cool. And then we do the same for sons, right? Get the son's heights and standard units. Son standard units. That let's just be lazy and I'll use the standard units function on that one. That's son's heights dot column son. I get the father's heights and standard units. I get the son's heights and standard units if that's the correlation value that I want to calculate. So there's the son's heights and standard units, the father's heights and standard units, and then I'll multiply them together. Father SU times son SU. And then I take all these values and I average them. So np.average, np.mean, either way, this is the correlation coefficient. That's how you calculate it. Same value. Okay? Cool. Any questions about that? See how this is a useful thing? You get these numbers, we can very quickly, I didn't have to draw any graphs. I could just see like, all right, what's the strongest correlated two variables here? And then I can explore further. Like, all right, let's actually draw the scatter plot. Okay, I do see a linearly associated thing. Maybe that can help me make a prediction engine. All right, you give me a father height, I will help predict the son height now. A father of a child that hasn't grown up yet, given all this data. That's beautiful. That's good knowledge, right? And I think that is what I wanted to say. Yeah. So again, our goal is we want to predict things. So this is another way of eventually being able to predict things. We found the strongest correlated things. We have a number for that now. It's the R value. It measures linear association, how well your data is tightly packed together on a line. Okay? And I think that's where I want to stop this time. I want to split this lecture up into 3 different lectures because this is a more important topic, I think. And so we've got time. Yeah, any last questions to be on the recording? So let me mark that this is where we stopped. And then we'll start next time with a, oops, to be continued. If I can spell continued. We'll start next time with a question where we explore a data set, we try to calculate some R values, and we'll get closer and closer to like building a way to predict based on them. So yeah, I think that's all that I wanted to say. Let me stop the recording.